Look up at the night sky tonight and imagine seeing something you have never seen before, a faint purple glow stretching from the horizon all the way to the top of the sky. Not the green shimmer of an aurora, not the orange haze of city lights, but a deep electric violet spreading silently across the upper atmosphere. That image may sound like science fiction, but according to the latest scientific data, something very unusual began happening only hours ago. Hello and welcome. Today is March 10th, 2026, and roughly 14 hours ago, instruments at the Mauna Kea Observatory in Hawaii detected an atmospheric event with only a 0.004% chance of occurring naturally. This was not a storm. It was not a fluctuation in solar wind. What researchers detected was a high-velocity injection of gas entering Earth's upper ionosphere right now. To understand the scale of what that means, imagine a tiny object in the vast emptiness of space, releasing a cloud of material so precisely that it intersects with a planet the size of Earth at exactly the right moment. That object is a comet-like body astronomers have been tracking for months, known as 3I Atlas. Earlier today, the spacecraft Gaia began sending back data, indicating that the object had performed something no one expected. Instead of simply shedding dust and ice the way ordinary comets do, it expelled a dense, coherent cloud of ionized gas directly along Earth's orbital path. Think about the odds of that for a moment. Space is unimaginably large. The chance that a random comet would release a concentrated gas cloud that just happens to intersect Earth at precisely the moment our planet crosses that path is astronomically small, roughly 1 in 4.8 billion. Yet the data says that is exactly what has happened. Confirmation soon followed from another powerful instrument, the James Webb Space Telescope. Its near-infrared spectrograph detected the chemical signature of the cloud. The results were startling. The gas contains large quantities of ionized strontium and iodine. When those elements interact with solar radiation and Earth's magnetic field, they emit light, specifically a glowing purple color in the upper atmosphere. That violet haze spreading across the sky isn't just beautiful. It is a direct signal that unusual chemistry is unfolding above our heads. But the color itself isn't what has scientists worried tonight. What keeps astrophysicists awake right now is the timing. The release of this gas happened exactly 38 minutes before the comet reached perihelion, its closest point to the Sun. In more than 4 million years of recorded cometary behavior, we have never observed a timing correlation that precise. Natural systems are messy and unpredictable. They rarely behave with such perfect alignment. Yet this event appears almost mechanical. When researchers plotted the trajectory of the gas cloud against Earth's orbit, an uncomfortable question emerged. Are we seeing the natural shedding of frozen material from a comet or something far more deliberate? If it is natural, then our understanding of cometary physics may be missing something fundamental. But if it is not natural, then something significant may have changed in our understanding of the universe just hours ago. Right now, satellites are detecting the disturbance. Amateur radio operators across the Pacific region are reporting unusual signal behavior. Instruments designed to monitor atmospheric chemistry are showing sudden spikes in ionized particles high above the planet. In other words, this is not just a distant astronomical curiosity anymore. The event is interacting directly with Earth's environment. To understand how we reached this point, we have to rewind the clock exactly 24 hours to March 8th at 8:15 UTC. That was the moment when the first hint of something strange appeared in a data packet arriving from the powerful radio observatory known as the Atacama Large Millimeter Submillimeter Array, or ALMA. Normally, comets behave in predictable ways. As they approach the sun, heat causes frozen water, carbon dioxide, and traces of ammonia to evaporate from the surface. The process is slow and steady. Astronomers often describe comets as dirty snowballs, slowly melting in sunlight. But what ALMA detected was nothing like that. Instead of a gradual leak of gas, the instruments recorded a sudden pulse, a violent burst of material expelled in less than 4 seconds. At first, scientists suspected a malfunction. Sensors fail, calibration errors happen, but within minutes, multiple observatories around the world began reporting the same signal. What initially looked like a simple anomaly was quickly turning into something far more serious. And that is where this story truly begins. Because once the confirmation arrived from 3 independent sources, the question was no longer whether something unusual had happened. The question was what exactly had just been launched toward Earth and why. If you want to know what those other observatories saw next, and why the data suddenly shifted from curiosity to global scientific concern, make sure you keep watching and subscribe so you don't miss the next part of this unfolding mystery. Because once the confirmation arrived from 3 independent sources, the question was no longer whether something unusual had happened. The question was what exactly had just been launched toward Earth and why. Within minutes of the initial signal from ALMA, another facility thousands of miles away picked up something that made scientists pause. The massive antennas of the Goldstone Deep Space Communications Complex in California detected a Doppler shift buried inside the background radio noise. That shift matched the signature of a dense plasma cloud moving through space at extraordinary speed. The timing was identical to the 4-second pulse recorded earlier. Then a third confirmation arrived. The sensitive instruments aboard the Hubble Space Telescope triggered an automated alert inside its cosmic origins spectrograph. The system classified the event as a magnitude 4 anomaly, meaning the spectral signal exceeded the thresholds normally associated with cometary activity. At almost the same moment, thousands of amateur astronomers across the Pacific region reported something they could see with their own telescopes. Observers from New Zealand to Japan watched as the brightness of 3I Atlas suddenly increased by a factor of 300. 3 completely different observation methods, radio detection, ultraviolet spectroscopy, and optical telescopes, had all arrived at the same conclusion. Something massive had just erupted from the surface of that object. And when scientists began analyzing the raw telemetry, the numbers became even harder to explain. Normally, gases escaping from a comet drift away at only a few kilometers per second. But the cloud launched from 3I, Atlas was clocked at roughly 42 kilometers per second relative to the nucleus. That is 10 times faster than the escape velocity expected from any known comet. To push material away at that speed, the object would need a powerful energy source. Frozen ice warmed by sunlight simply cannot do that. In practical terms, such a burst would require something closer to a propulsion event than a natural evaporation. It would require pressure buildup, rapid release, and enormous internal energy. In other words, a mechanism. The speed alone raised eyebrows across the astronomical community, but it was only the first sign that something about this event did not follow the usual rules. As scientists continued to track the cloud during the night of March 8th, another anomaly appeared. Under normal physics, gas released into empty space spreads out immediately. Entropy ensures that particles disperse in all directions, becoming thinner and weaker with time. It is similar to opening a bottle of perfume in a room. At first the scent is strong near the source, but eventually it spreads until it fades completely. The same principle applies in the vacuum of space. Gas clouds expand and dissipate. Yet this cloud did not behave that way. Between 12 and 18 UTC, measurements showed that the cloud remained remarkably compact. Instead of thinning into a diffuse mist, it maintained a nearly perfect spherical shape. It traveled across millions of kilometers like a projectile rather than a drifting cloud. Data from the GOES-19 indicated almost no loss of density during the journey toward Earth's magnetosphere. That result alone left atmospheric physicists stunned. A cloud of ionized gas should not stay together for 6 hours in open space. There is simply nothing to hold it in place. But the readings suggested something extraordinary. The plasma appeared to be magnetically confined, as if invisible forces were preventing it from dispersing. And that brings us to the most visible part of the event, the color. Observers across the Pacific and parts of the Americas began reporting a strange violet glow spreading across the night sky. At first glance, it looked like an aurora, but the color was wrong. Most auroras are green or red because they come from oxygen and nitrogen interacting with solar particles. Those are familiar atmospheric processes. Purple auroras, however, are extremely rare and require a very specific chemical composition. At around 22 UTC last night, the answer finally arrived when spectroscopic data from the W.M. Keck Observatory confirmed the identity of the gas. The cloud was not made of water vapor or carbon dioxide. It was dominated by ionized strontium and iodine. In laboratory experiments, strontium compounds burn with a bright red-violet flame. When the element becomes ionized in the upper atmosphere and interacts with solar ultraviolet radiation, that glow shifts into a deep purple tone. That is exactly the color now appearing in Earth's ionosphere. But the real shock came when scientists calculated the concentration of strontium in the cloud. In decades of comet studies, including data from the Rosetta, the highest strontium levels ever measured in comet material were about 0.001%. The cloud surrounding Earth right now contains nearly 14% strontium. 14%. To put that into perspective, imagine discovering a block of Antarctic ice that contains 14% pure titanium. No geologist would call that natural. They would assume someone put it there. The sheer quantity of material needed to tint Earth's upper atmosphere purple across an entire hemisphere is enormous. Scientists estimate millions of tons of highly specific elements were injected into space with incredible precision. And just when researchers thought they understood the situation, the behavior of the cloud changed again. Instead of drifting away from the sun, like every other cometary plume, the purple haze began moving sideways, almost perpendicular to the solar wind itself. That shouldn't happen. The solar wind travels outward from the sun at roughly 400 kilometers per second, and almost everything in the solar system follows its direction. But this cloud is doing something different. It is moving against that flow. The more data scientists gather, the stranger the picture becomes. The cloud has speed, structure, and a chemical signature that suggests something manufactured rather than natural. When several researchers at the NASA Goddard Institute for Space Studies compared their measurements, they arrived at the same uneasy conclusion. Earth's atmosphere appears to be reacting to a foreign substance. And that raises a question no one is prepared to answer yet. If this cloud is artificial, what is it actually doing here? Because when scientists looked closer at the interaction between iodine in the cloud and Earth's ozone layer, they discovered something remarkable. The mixture absorbs ultraviolet radiation. It acts like a filter, reducing the intensity of certain wavelengths of sunlight reaching the planet. In other words, the cloud might be dimming the sunday. For decades, humanity searched the universe for signals, radio messages, laser pulses, or mathematical codes from distant civilizations. We assumed contact would arrive as a communication. But what if it arrives as a physical delivery instead? Right now, as instruments aboard the International Space Station continue monitoring the cloud, scientists are detecting something else, a faint new frequency coming from inside the purple haze itself. The discovery phase is over. We have entered the active event phase, and what the next set of measurements reveals will push this story into territory no one expected. If you want to see what happened when the clouds suddenly began slowing down in open space, something that should be physically impossible, stay with me and subscribe, because the next part reveals the moment the laws of physics themselves seemed to break. And what the next set of measurements revealed pushed the entire investigation into territory that most scientists would normally associate with theoretical discussions, not real-time observations. Because shortly after the mysterious frequency was detected inside the purple haze, researchers noticed something even more troubling. The cloud began to slow down. In space, that should not happen. According to the most basic rule of motion, what we know is Newton's first law, an object moving through a vacuum should continue moving unless an external force acts upon it. There is no air resistance in the exosphere, no friction to drain energy from a drifting plasma cloud. Yet, at around 2 UTC this morning, the numbers showed the velocity of the cloud dropping dramatically. Only hours earlier, it had been traveling at roughly 42 kilometers per second after leaving the interstellar object known as 3I, Atlas. But now the data streams coming from orbital instruments showed the cloud losing speed rapidly. Within 45 minutes, it slowed almost to a standstill over the Pacific Ocean. To understand how extraordinary that is, scientists calculated the estimated mass of the cloud based on spectroscopic density measurements. The result was staggering, around 33 million tons of material. Stopping something that massive would require an enormous force, the kind of braking effect usually associated with planetary gravity or intense magnetic fields. Naturally, researchers looked for those explanations first. Magnetometers aboard the GOES 19 were checked immediately. If the cloud had interacted with Earth's magnetic field strongly enough to slow down, those sensors should have recorded a dramatic spike. But the readings came back normal. No unusual magnetic disturbance, no energy burst, no signal of an external force acting on the cloud. The only remaining explanation was unsettling. The cloud appeared to have slowed itself. Even more surprising was what happened next. Instead of drifting randomly through the upper atmosphere, the cloud stabilized at an altitude of about 400 kilometers, almost exactly the same altitude where the International Space Station circles the planet. In orbital mechanics, achieving that kind of stable position requires careful calculations and controlled velocity adjustments. Engineers call it orbital insertion, yet here was a cloud of gas apparently performing that maneuver on its own. At this point, the scientific discussion began shifting from anomaly to possibility. Was the cloud behaving like a natural plasma structure, or was it functioning more like a controlled system? Then another discovery complicated the picture further. Instruments aboard the International Space Station were analyzing particles drifting through the outer edge of the cloud when the onboard mass spectrometers identified a third element in the mixture. Earlier observations from the W.M. Keck Observatory had already confirmed high concentrations of strontium and iodine, but the new readings detected something else, xenon-135. For researchers familiar with nuclear physics, that isotope carries serious implications. Xenon-135 is a powerful neutron absorber commonly produced during nuclear fission reactions. In nuclear reactors, it plays a crucial role because it can shut down chain reactions by absorbing neutrons. Finding it in space would already be unusual, but finding it inside a cometary gas cloud is almost impossible. The reason comes down to time. Xenon-135 has a half-life of roughly 9 hours. That means any supply of it decays quickly. If scientists are detecting Xenon-135 now, it must have been produced recently, within hours, not centuries. In other words, The isotope appears to have formed after the cloud left the comet. That detail raised a question that few researchers were comfortable asking out loud. If xenon 135 is being generated inside the cloud itself, what kind of process is producing it? Cosmic rays can occasionally create rare isotopes through high-energy interactions, but calculations show the probability of xenon 135 forming naturally inside a cold, drifting plasma cloud is vanishingly small, less than 1 chance in 10 to the power of 50. In statistical terms, that number effectively means 0. So scientists are now looking at a structure in Earth's upper atmosphere that can slow itself down, hold a stable orbit, and generate short-lived nuclear isotopes internally. At this stage of the investigation, many researchers have stopped referring to it as a simple gas cloud. Instead, they are beginning to use a different word, system. Because when you analyze the absorption spectrum of the mixture strontium, iodine, and xenon 135, it reveals a specific property. That combination absorbs a narrow band of ultraviolet radiation from the sun, particularly in the UVC range. Those wavelengths are normally blocked by Earth's ozone layer before reaching the surface, but in the upper atmosphere they still exist in measurable quantities. The cloud appears to be filtering them. Imagine a gigantic atmospheric lens floating hundreds of kilometers above the Pacific Ocean, selectively adjusting the radiation passing through it. That is the effect scientists are now measuring. But the most surprising discovery came around 4:30 UTC, when the cloud began doing something completely unexpected. It started pulsing. Sensors measuring electromagnetic fluctuations detected a rhythmic oscillation spreading through the plasma. The frequency of that pulse was extremely precise, 7.83 Hz. For geophysicists, that number is instantly recognizable. It is the primary frequency of the Schumann resonance, the natural electromagnetic vibration that exists between Earth's surface and the ionosphere. In simple terms, the planet itself resonates at roughly that frequency due to global lightning activity. It is sometimes described as the electrical heartbeat of Earth. And now this cloud was matching it. When two oscillating systems share the same frequency, a phenomenon known as resonance occurs. Energy can transfer between them efficiently, amplifying the effect. It is similar to the way a singer can shatter a glass by hitting the right note. The vibration builds until the structure cannot contain it. Researchers watching the data streams began noticing that as the cloud pulsed at 7.83 Hz, the purple glow across the sky intensified. At the same time, measurements showed the electron density in the upper atmosphere rising sharply, nearly 400% higher than normal levels in just a few hours. This change has immediate consequences. Signals used by navigation satellites rely on predictable ionospheric conditions. When the electron density shifts dramatically, GPS accuracy begins to degrade. Already, some navigation systems are showing minor positional drift, while high-frequency radio communications across parts of the southern hemisphere are experiencing brief outages. In other words, the electromagnetic environment of our planet is starting to change. Scientists have tried to imagine natural explanations for this chain of events, but each step seems increasingly unlikely. A comet releases a gas cloud. The cloud travels toward Earth without dispersing. It slows down on its own, parks in orbit, contains nuclear byproducts, and resonates with Earth's natural frequency. At some point, coincidence stops being a convincing explanation. The scale of what might be happening is extraordinary. If we could see magnetic field lines with our eyes, researchers believe we would notice them bending slightly around the cloud, forming a kind of protective bubble in space. And inside that bubble, radar measurements suggest something else may be developing. Because the radar cross-section of the center of the cloud has begun to increase. Something appears to be forming inside the purple haze. The xenon continues reacting, the strontium continues glowing, and the core temperature measured indirectly through infrared instruments is rising faster than expected. Which leads to a possibility that sounds almost impossible. The cloud itself might not be the event. It might be the construction site. And if that is true, the next set of observations could reveal what exactly is being assembled above our planet right now. Stay with me and subscribe, because in the next part we'll look at the moment scientists realized the cloud wasn't just floating in our atmosphere, it was focusing energy toward a specific point on Earth, and that realization changed everything. Up to that point, scientists were trying to understand the cloud as a strange atmospheric phenomenon, something unusual, maybe even unprecedented, but still explainable within the boundaries of physics. But the moment the next set of data arrived, the situation took a different turn. Because while researchers were analyzing the increasing heat signature at the center of the purple cloud, another observatory detected something completely unexpected. At 6:15 UTC, a signal came from the high-energy stereoscopic system, better known as HESS. This array of telescopes normally studies extremely energetic cosmic events such as supernova remnants and distant gamma-ray bursts. It was never designed to monitor atmospheric anomalies above Earth. But that morning, the detectors recorded a sudden concentration of incoming solar particles that appeared to be interacting with the cloud above the Pacific. What they saw looked almost like a lens forming in the sky. Imagine holding a magnifying glass under sunlight and focusing the rays into a single bright point. That is exactly what the plasma cloud appeared to be doing with the solar wind. Instead of letting charged particles pass through randomly, the cloud was channeling them into a narrow, coherent beam aimed directly toward the surface of Earth. This was not passive reflection or scattering. The data suggested active redirection of solar plasma. Within minutes, scientists began examining the beam's structure more closely. At first, it looked like noise, random fluctuations in particle density. But then researchers noticed something strange repeating inside the signal. The pattern was mathematical. It followed the sequence 1, 1, 2, 3, 5, 8, 13, continuing forward exactly as mathematicians would recognize it. The Fibonacci sequence. That discovery forced the moment of silence inside more than one control room. Patterns appear everywhere in nature. Spirals in shells, the structure of flowers, the arms of galaxies. But nature does not transmit the Fibonacci sequence as a repeating digital pattern embedded in a beam of high-energy particles. To produce something like that requires intention. At that point, the investigation shifted from physics toward geometry. If the cloud was directing energy toward Earth, the next question was obvious. Where exactly was the beam pointing? Researchers at the high-energy stereoscopic system began triangulating the trajectory. By combining particle detection angles with satellite tracking data, they slowly narrowed down the endpoint. The results surprised everyone. The beam was not targeting a city, a continent, or even a populated region. Instead, it was aimed at a point in the South Pacific Ocean, located at approximately 48 degrees south and 123 degrees west. That location has a name known mostly to oceanographers and space agencies. Point Nemo. Point Nemo is the most remote place in the ocean. It is farther from land than any other location on Earth. The nearest humans are often astronauts orbiting overhead aboard the International Space Station rather than anyone on the surface. Space agencies even use this region as a disposal zone for decommissioned satellites and spacecraft because it is so isolated. In other words, if something wanted to interact with Earth while avoiding immediate human interference, Point Nemo would be the perfect location. The moment the coordinates were confirmed, scientists began checking environmental data from the region. Oceanographic buoys and satellite sensors monitor water temperature constantly. When researchers examined the most recent readings, they found something that made the situation even more concerning.